Let us start lecture 20. The course is phase diagrams in single component and binary systems. And today we will consider, we will continue our same topic what we have done in the last lecture. It is basically phase diagram in water system. And in the last lecture we tried to understand that when a line, two phase boundary line enters into single phase, what happens to the to its existence. In fact, we have tried to understand with the help of equilibrium hierarchy. Okay. And we have seen at 2 points, one at triple point, another at a pressure above triple point. And here we have considered a constant pressure, and then we have started looking at the situation or the relation, interrelation between free energy temperature plot for both all the three phases, solid liquid, liquid vapor as well as solid vapor. And we have seen that how the solid vapor boundary line, when it that particular equilibrium line, when it enters into the liquid phase, every point on those lines will be lying above the free energy of a liquid. That is what those all points will be metastable. And we have also seen when we try to indicate metastable points or situation in a phase diagram, we show it with a dotted line. Its existence is there, but it is not a stable existence, rather metastable existence. So, we will continue there, and then we try to see what happens if we take a pressure below triple point, and then we will see that how the relation between all three G versus T plots for solid, vapor and liquid appear on a G versus T plots, G versus T plane actually. So, what we have done in the last class, this is the topic, the same topic, phase diagram in single component system. Last class what we have seen, just a kind of, we have seen this is liquid, this is liquid, this is solid, this is vapor, and when the solid vapor line enters into liquid, it becomes dotted. So, we have considered two pressure, one pressure was this, another pressure was this is P prime, okay. And the P prime, the diagram look like this, G versus T plot look like this. Let me just quickly plot it at P prime. So, 3 points are there. So, those were extended over G versus T plot. So, this becomes T LV, this become T SP and this become T SL. Now, we saw like this. This is solid line GS. So, then we drew liquid line. This becomes bit tricky, you have to practice a bit, okay, like this. Okay, so, this is GV, this is GL, and we saw that this would be my stability free energy line. This would be the red line is basically my stability line, and we have understood with the hierarchy, equilibrium hierarchy. Now, and you could see that all those 3 points are placed here, okay, all those 3 equilibrium points. Now, what we will do, we will try to, as we have seen that is what this becomes dotted. Now, we have to see whether these 2 lines are also becoming dotted, that means metastable or not. So, in order to see that, let me just draw that particular plot again. This is T, this is P, Let me extend this one a bit. So, I will take a pressure which is below triple point pressure. Let me take this P double prime pressure, and corresponding free energy temperature plot will be drawn. So, let me extend those transformation points, those cross points, these 3 points will extend over G versus T plot. So, this should be T SL because it is lying on SL boundary, phase boundary. This is LV and this is SV. Okay. So, then this point which is lying on SV line, so that should be T SV, and this point which is lying on LV line, this should be T LV. Okay. Now, first let me draw solid line with a lowest slope GS. Now, the next one would be I have to draw vapor line GV which should pass through this point. So, if I draw the vapor line, okay, this is GV. Now, the liquid line should pass through this and this. The liquid free energy line with a little higher slope than solid. Okay. This is GL. Okay. So, that means here GS equal to GL, at this point GL equal to GV, and then we have a point here which indicate GS equal to GV. So, that should be the plot. Now, let us understand hierarchy, equilibrium hierarchy. Let us say I go below this, below TLV. So, if I go below TLV, I see that GV is greater than GL greater than GS. That means solid phase has the lowest free energy. So, solid stable, solid is stable, T less than TLV. Okay. Now, let us go between these two, which is between TLV and STSV. So, there I see that GL has the highest value, then GV, then GS. So, solid again has the highest stability, lowest free energy value. So, between TLV and TSB, I see solid again is stable. So, less than TSB, so that means from these two I see that this one as well as this one, I could see that T less than TSB, solid is stable. So, that means any point, that means this particular point which is lying on liquid vapor surface should be metastable. So, I can say T less than TSP, P prime, double prime and TLV, that point should be metastable. And if I see carefully that all the points appearing on this particular line until triple point, all if I do all those diagrams below triple point, I will see that particular situation, that pressure and temperature corresponding to the points appearing on liquid vapor line below the pressure, triple point pressure, would always be metastable. Okay. So, then I am seeing that this line should be dotted up to triple point. Now, let us check the other things. Let me see between these two. So, that means between TSV and TSL, I see that GL greater than GS greater than GV. So, this means vapor is stable. Similarly, if I take anything right side of TSL, so T greater than TSL, I see the hierarchy which is GS greater than GL greater than GV. So, again I see vapor is stable, because vapor free energy has the lowest value. So, that means any point appearing beyond TSL, T greater than TSV, where everything would be vapor will be stable. And you see this particular point which is appearing on solid liquid boundary equilibrium line. So, those point again becomes metastable. So, I see that this gives me a conclusion that when this happens, then P double prime TSL, that particular point is metastable. So, that means if I take any pressure, if I keep fixing pressure below T triple point, so that means from below this, every point lying on solid liquid line all the points will be metastable. So, that means this particular line also becoming dotted, because we know that metastable line should be drawn in a dotted fashion. That existence is there, but that is metastable existence. So, if I try to, from that understanding, if I try to plot again this revised plot, so this plot would become this one, then this one, and then vapor is this is solid, liquid, vapor, and then all those lines which are entering into single phase zone will be dotted. Okay. So, this is the complete situation of those boundary lines, equilibrium lines on a pressure temperature plots. This is basically the phase diagram, complete phase diagram of water. Fine. So, this is solid liquid equilibrium line, this is liquid vapor equilibrium line, and this is solid vapor equilibrium line. Okay. So, that is what some of the lines appearing in a phase diagram, on a phase diagram as dotted, please realize that those have metastable existence. Those are not out of the system, rather those are there, but they would have their metastable existence. Okay. So, this particular existence part, why those lines are becoming dotted, we could show it with the help of G versus T plot, okay. And that time we have fixed the pressure. Okay. For example, here we have fixed pressure which is double prime, which is less than triple point pressure T P T, fine. And the previous case we have fixed the pressure, this particular P prime pressure is always greater than P T, this is let us say P T, triple point pressure. Okay. So, accordingly we could sense which one is becoming dotted and which one is becoming solid, and solid lines are all stable lines. Okay. That means, that case that particular phase would appear as a stable phase. Now, let us show it with respect to another plot, which is basically a free energy plot, G versus P plot rather than G versus T plot. So, when we shift from G versus T to G versus P plot, we have to fix temperature as a constant value. Okay. So, that one if I try to show it, okay, so we will show it for one instance, and then the rest of the thing will be explained, will be put up, and you can also try it yourself during the problem solving sessions. So, now we are doing when we keep when temperature is fixed. So, and this metastability can be explained with the help of G versus P plot. So, now we again come back to the basic equation V dP minus S dt. So, we are fixing temperature. So, it becomes delta G delta P for solid equal to V S, then delta G dou G del P liquid and constant temperature would be equal to V L, and dou G dou P vapor constant T would be equal to V V. In case of water, interesting thing that happens is basically V S greater than V L and V V is greater than V S. So, when liquid water transforms to solid water, volume expands and vapor phase of water has the maximum volume. So, this needs to be considered while plotting G versus P plots, and that time every plot would be having positive slope, because this vapor, these are all positive values. So, these are all greater than 0, okay, and there is only positive sign. So, the slopes will be positive. So, let me just plot. While doing that, we have to modify the plot. So, this side would be pressure and this side would be temperature, and this temperature increases this way and the pressure increases this way. Okay. So, the plot would look like this. So, this would be my that case, this side would be solid, this side would be liquid and this side would be vapor. Okay. Now, let us see whether it is going as per our plan. Now, if temperature decreases and increases pressure, for example, let us take solid liquid line. So, if I increase the pressure, my melting point should decrease. So, you see this way is decrease in temperature. So, the temperature gradually decreases. Fine. So, for example, vapor, if I increase the pressure, then temperature, transformation temperature should increase, because when I plot this way, it looks like this. So, this is liquid, vapor, solid. So, if I increase the pressure, temperature increases for both solid vapor as well as liquid vapor line. You see, this is my liquid vapor line and this is the solid vapor line, and if I increase the pressure, temperature, transformation temperature or sublimation temperature increases as well as evaporation temperature also increases. So, that means plot is fine. So, you have to just change a bit. Now, triple point is this one. So, that time I am fixing the temperature. So, this triple point is let us say T, and T indicates this subscript T indicates the triple, fine. Now, I take a temperature, fixed temperature above triple point. So, I take a temperature like this, okay, which is T prime. If I take that, let us take a plot which is pre versus G at T equal to T prime. Now, you see that constant temperature are cutting those equilibrium lines at those three locations. I will project them over pressure axis. So, this becomes P SL, this becomes P LV and this becomes P SV. Okay, fine. So, instead of temperature, I am doing it in terms of pressure. So, now we have to draw. So, which one would have the highest slope? Because we know vapor phase has the highest molar volume. So, that slope would be the maximum, because when I try to look at this, so the plot becomes like this, G versus P at a constant temperature, the plot is upward, okay, and the slope is nothing but V, molar volume, if I talk about 1 molar volume, 1 mole. So, now accordingly here also the situation would appear. Since the vapor line we are drawing with green color, let me draw that first, which is the maximum slope. Okay. So, this is GV. This point corresponds to solid vapor. So, the solid vapor line should pass through this, the GS line, and it would have higher slope than the liquid line, because that molar volume of solid is more than molar volume of liquid in case of water. So, this would have little higher slope. Okay. So, this is GS. Now, GL should have the lowest slope, and that GL should pass through this point and this point. Okay. So, that GL line should pass through this. So, this is GL, this is GS, and you see GL has the lowest slope, GS has the in between slope between vapor and liquid, and vapor has the highest slope. And all those three equilibrium points, as per those points lying on equilibrium boundary lines, are reflected here. Okay. Now, let us see. So, one point is this one, another point is this one, another point is this one. Fine. Let us see the equilibrium now, hierarchy, equilibrium hierarchy. P less than PSP, if I see that, then, or rather GL is greater than GS greater than GV. So, vapor is stable. So, then P greater than PSL, if I try to see, so then GV greater than GS greater than GL. So, liquid has the lowest free energy. So, liquid stable, liquid is stable. Now, we have to see what happens in between PSP and PSL. So, first let us see this particular zone where, which is between PSP to PLV. So, there I see GL greater than GV greater than GS. So, solid phase is stable. And again, if I try to look at between these two, PLV to PSL, again I see that GV greater than GL greater than GS. Again, solid is stable. So, that means any at that pressure, that particular this point, that means PLV and T prime, that is the point lying on liquid vapor equilibrium boundary line. So, this point is metastable. Since I see, so between PSV to PSL, all the cases solid has the lowest free energy. So, if I try to draw the free energy which are stable with the red color from left to right, so that particular thing would appear like this. Okay. So, that means less than PSP, vapor would be stable, between PSP to PSL, solid will be stable, and then beyond PSL, we see liquid would be stable, and exactly that corroborates the phase diagram. Okay. So, in these 2 points, solid is stable, right side of it liquid is stable, left side of it vapor is stable. So, the any point lying on liquid vapor boundary line beyond the temperature corresponding to triple point would always be metastable. So, that means this line should be drawn in the phase diagram as a dotted line, okay, up till what? Up till the triple point. Okay. So, like that way you can also check what happens if I take any temperature below temperature triple point temperature. You will also experience that two lines will be dotted. So, then you will see that this line would be dotted, this line would be dotted, and this line would be dotted. Okay. So, only the liquid line would be having solid appearance. Fine. So, like that way one can calculate, one can find out which line would become dotted on a phase diagram. Fine. So, this particular temperature, which is let us say T double prime, I wish you do that particular analysis, and by doing this particular plot between G versus P at that constant temperature T double prime, and should see that whether any point lying on this liquid vapor solid vapor line or solid liquid line are actually becoming metastable or not. Fine. Okay. That is the, you should get it. Okay. So, now let me conclude this lecture by saying that that phase diagram is a reflection of phase equilibria in case of single phase single component system, and here we see 3 phases are actually having their inter equilibrium, and then finally we are getting those lines, and some of the lines would appear as dotted, which reflect that metastability of those phases in that zone, and those metastability line is actually entering into single phase zone. So, remember, and that also a kind of way to understand that whether that phase diagram is drawn properly or not. So, if you see that any 2 phase boundary line in a phase diagram, if it enters into single phase, that means you are right about your phase diagram. Okay. So, we will continue on the same diagram, because we will now try to understand some of the physical aspects or the physical examples which can be explained through this phase diagram. So, one of the examples is basically the cavitation damage happens on impeller blades or ship hulls, ship blades, basically that propeller blade, not hulls, propeller blades. So, why that particular cavitation happens, and that has a relation to this phase diagram. So, we will try to analyze that. Okay. For example, we can also analyze that when some mountaineer go to a high altitude area, let us say a mountaineer going to Everest, that time they have to eat from the pressure cooker. Okay. So, they cannot let it cool down, because why that pressure cooker is needed to cook properly cook food at high altitude area. So, we will try to explain through this phase diagram. So, the next class will be concentrated on that, examples of this phase diagram, and then we will also examples of some of the phenomena which can be explained through phase diagram, and then also we will touch upon the phase diagram in case of CO2 system. Okay. CO2 system, you will see it will be little different than water system, because CO2 system we do not have that anomaly, that is the solid volume, solid CO2 volume is not greater than the liquid CO2 values. Okay. So, with that we will have little difference. So, we will also look into that part. So, let me stop here. Thank you very much.